Imagine you are sitting in a dark room, with only the dim light from the projector screen flickering with distant bright dots, the gentle hum of the projector sounding like the breath of the universe. Before your eyes, billions of stars quietly twinkle, each one a story spanning billions of years, filled with silent battles against gravity, dazzling explosions, and tragic deaths. The universe is not merely a cold empty space, but a vibrant ocean, where everything originated from a massive explosion known as the Big Bang, which occurred approximately 13.8 billion years ago, according to the most recent estimates derived from observations by the James Webb Space Telescope, launched in the year 2021. This extraordinary instrument, orbiting far from Earth, has peered into the deepest recesses of cosmic history, revealing galaxies forming just hundreds of millions of years after the Big Bang, challenging scientists to refine models of the early universe's expansion. Recent data from 2025, including studies of ancient light from quasars and starburst galaxies, suggest that while the core age estimate holds steady at around 13.8 billion years, the rate of cosmic expansion might be slightly faster than previously thought, easing long-standing tensions in measurements known as the Hubble constant. That singular beginning marked the birth of all fundamental particles, every atom, every star, and every galaxy from a singular point of extreme heat and density, with temperatures soaring to trillions of degrees Kelvin. Picture the overwhelming sensation, a silent yet resounding explosion rippling through expanding space, birthing vast clouds of gas, colorful nebulae that we observe through telescopes like the Hubble Space Telescope or ground-based observatories such as the Keck Observatory in Hawaii, where massive mirrors capture light that has traveled billions of years to reach us, unveiling structures like the pillars of creation, towering columns of interstellar dust and gas where new stars are even now igniting. Now, let us venture deeper into the lives of stars themselves, those colossal spheres of plasma where gravity serves as an unrelenting adversary. Each star, from its birth to its demise, endures a ceaseless struggle. Envision gravity as an enormous invisible hand, squeezing inward from all directions toward the star's core, attempting to crush it into a minuscule point. Yet the star does not yield so easily. Within its core, fierce nuclear fusion reactions unfold. Hydrogen, the most abundant element in the universe comprising about 75% of its total mass, is heated to tens of millions of degrees Kelvin and transformed into helium through nuclear synthesis. This process unleashes colossal energy in the form of heat and light, propelling matter outward to counter the compressive force of gravity. This represents the stable phase, enduring billions of years for stars akin to our Sun. You might imagine the fictional sound, the hiss of boiling plasma, the crackling pops of atomic nuclei colliding, and the blinding light radiating into the frigid void of space. Stars form within vast molecular clouds of gas and dust, spanning hundreds of light-years and containing masses from 1,000 to 10 million times that of the Sun. Gravity causes regions to collapse, heating the material until it reaches ignition temperatures around 8 million degrees Kelvin, marking the transition from protostar to main sequence star, where 90% of a star's life is spent fusing hydrogen stably. For massive stars, this phase shortens dramatically, lasting mere millions of years due to their voracious fuel consumption. Our universe harbors hundreds of billions of galaxies, and the Milky Way alone contains approximately 200 to 400 billion stars. Every hour, somewhere in the immense cosmos, a star concludes its life cycle. In the Milky Way, the rate is more modest, only 1 to 2 supernovae per century, based on data from observations by the Chandra X-ray Observatory, which has catalogued remnants like Cassiopeia A young supernova exploded around 350 years ago, its shock waves still visible as glowing filaments of hot gas. As hydrogen fuel depletes, the star contracts. For those 8 times more massive than the Sun, the core proceeds to fuse helium into carbon and oxygen, then neon, magnesium, and ultimately iron. Iron marks the endpoint. Fusing iron consumes energy rather than producing it. At this juncture, gravity prevails. The outer layers compress violently before rebounding in a supernova explosion, a fireball brighter than its host galaxy, releasing energy equivalent to billions of nuclear bombs. Envision the spectacle. A serene star suddenly swells, then shatters, ejecting superheated gas and dust at thousands of degrees, illuminating surrounding space for weeks. Remnants may form ultradense neutron stars, where a teaspoon of matter weighs as much as Mount Everest, or black holes, where gravity is so intense that even light cannot escape. These explosions also seed the cosmos with heavier elements, forging the building blocks for planets and life, as observed in spectra from distant supernovae that reveal iron peaks confirming core collapse mechanisms. To grasp this more fully, return to origins. A star like our Sun emerges from a nebula, enormous clouds of gas and dust spanning hundreds of light-years, chilled to mere tens of degrees Kelvin above absolute zero. Gravity draws matter together, forming a warming central mass. After roughly 10 million years, the core temperature hits 8 million degrees Kelvin, igniting nuclear fusion. Hydrogen constitutes 90% of the composition, helium 10%, and heavier elements just 1%. Larger stars burn fuel more rapidly, living shorter lives, mere millions of years compared to the Sun's 10 billion. The latest updates from the European Space Agency's Gaia mission, launched in 2013, have mapped over 1 billion stars in 3 dimensions as of 2025, confirming the Milky Way's spiral structure with 4 major arms, positioning our Sun in the Orion Arm about 26,000 light-years from the center. Recent visualizations from Gaia even allow virtual flights through star-forming nurseries, highlighting clusters like the trapezium in Orion where massive O-type stars, the hottest and most luminous, dominate and trigger further births through their radiation pressure. But stars are not the sole narrative. Let us shift to another enigma: petroleum, the fossil fuel that reshaped human history. Picture yourself standing beside an offshore oil rig, salty sea winds whipping across, the clamor of oil pumps echoing, the scent of crude oil glistening under sunlight. Petroleum forms from ancient marine microorganisms and algae that perished hundreds of millions of years ago, buried under sedimentary layers, cooked at temperatures between 100 and 150 degrees Celsius through geological processes. Primarily composed of hydrocarbons, it differs from coal derived from terrestrial plants. From antiquity, humans utilized raw oil for illumination or medicine. The first oil refinery was constructed in 1851 in Poland, and industrial extraction commenced in 1858 in Canada. By 2011, humanity had consumed 1.2 trillion barrels of oil. Presently, annual consumption stands at about 32 billion barrels, per the International Energy Agency's 2024 report. Yet reserves are finite. According to the BP Statistical Review of World Energy for 2025, at current rates, conventional oil could deplete in roughly 50 years, though technologies like hydraulic fracturing have unlocked unconventional sources, extending accessible volumes by an estimated 20%. Global demand peaked in 2025 in both primary scenarios of the BP Energy Outlook, with non-OPEC Plus producers bearing the brunt of declines, while coal consumption falls amid rising renewables. Extracting oil grows ever more arduous. In the 1950s, the energy return on investment was 1 to 100, expending 1 barrel to retrieve 100. Today, for offshore platforms costing hundreds of millions of dollars, it ranges from 1 to 5 or 1 to 3. Petroleum represents solar energy accumulated over 500 million to 1 billion years, which we combust in mere centuries, liberating greenhouse gases amassed over millions of years. Atmospheric carbon dioxide concentrations surpassed 410 parts per million in 2025, as measured at the Mauna Loa Observatory, exceeding the safe threshold of 350 parts per million. Annually, fossil fuels emit approximately 21.3 billion tons of carbon dioxide. Half is absorbed by oceans and forests, the remainder accumulates, fueling climate change. Imagine the anxiety: skies choked with smog, rising temperatures, fiercer storms and floods, and future generations confronting desertification and sea level rise projected to inundate coastal cities by 2 meters by 2100. Earth has endured at least 5 major mass extinctions and 3 great ice ages, per geological records. Now, we accelerate the carbon cycle, incinerating a billion-year legacy in an instant. Natural disasters, from hurricanes to droughts and floods, intensify, with humans as primary victims, as evidenced by 2025's record-breaking heatwaves linked to fossil emissions. Fossil fuels are Earth's gift, yet at the cost of instability. Now, let us soar farther to black holes, cosmic monsters. To gauge their mass, astronomers track orbital paths of surrounding stars. Velocities reach 16 million kilometers per hour near the Milky Way's central black hole, Sagittarius A star, weighing 4 million solar masses, per Event Horizon Telescope observations from 2019, with 2025 updates revealing polarized light images and hints of outflowing winds. Long-predicted gas streams finally detected, suggesting accretion disk dynamics more complex than models anticipated. Gravity, the weakest of the four fundamental forces, electromagnetic, strong nuclear, weak nuclear, and gravity, dominates on cosmic scales. An intriguing concept: white holes, counterparts to black holes. Per Kerr metric theories, a zero-mass singularity might eject matter like a fountain. But our matter-filled universe precludes them. Any infalling particle collapses the structure. Hawking radiation, theorized in 1974, indicates black holes evaporate slowly over trillions of billions of years. A captivating hypothesis: the Big Bang as a white hole eruption from a minuscule black hole in a parent universe, mathematically plausible yet evoking science fiction. Regarding life, Earth formed 4.5 billion years ago, earliest life around 3.8 billion years prior, via Greenland's stromatolite fossils, with 2025 reviews of 3.7 billion-year-old Ishwa supracrustal belt structures pushing timelines back 220 million years, suggesting microbial mats in metadolostones as evidence of ancient biofilms. Hypothesis: amino acids in primordial ponds reacted over millions of years to form proteins, then cells. Or asteroids delivered organics via panspermia. Water is key, present system-wide. Mars harbors subsurface ice, Jupiter's Europa a liquid ocean beneath 30 kilometers of ice, per the Europa Clipper mission launched in 2024, now en route with gravity assists from Mars in 2025 and Earth in 2026, equipped with 9 instruments to probe habitability through 49 flybys. The Solar System. The Sun comprises 99.8% of mass, diameter 1.4 million kilometers. Planets: Mercury, daytime 430 degrees Celsius, nighttime minus 173, Venus, hottest at 470 degrees with thick carbon dioxide atmosphere. Earth, sole bearer of life. Mars, explored by Perseverance rover since 2021, Jupiter, Great Red Spot Storm twice Earth's size, Saturn, rings spanning 300,000 kilometers, Moon Titan with methane atmosphere. Cassini mission ended 2017 yielding invaluable data. The Oort cloud at the edge, 1 light-year wide. Extraterrestrial life might rely on silicon for extreme heat tolerance or thrive in gas giant clouds. We seek via SETI, future multiplanetary. Savor each moment on this blue planet, for the universe's mysteries await.